Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome. We are here to change our world with chemistry. We are on unit number 15. We are going to talk about entropy and free energy. Oh, thank you for tuning in. Make sure you put your calculator and pen and book very nearby. So our lesson today is going to talk about definition of entropy and very many other things about Gibbs free energy and our lesson objectives. By the end of this lesson, students should be able to define entropy, use entropy values to determine the feasibility of reaction. And when we talk about reaction feasibility, we are talking about the possibility. We are talking about the possibility of the reaction. So when you are dealing with the possibility of reaction, we normally use this energy term we call free energy or Gibbs free what? Energy. So what is entropy? So entropy is a quantitative measure of microscopic disorder for a system. So it's actually a measure of disorder or randomness of our system. So when molecules are mixed together, they normally move. As they move, we can measure their movement using this energy term we call entropy. So entropy is an energy term, as I have told you. So our units are joules per Kelvin, or we say joules per Kelvin per mole. So at standard conditions of 298 Kelvin and then in their normal physical state. So some of our standard entropy values are here. We have diamond, which is 2.4. No, diamond is very hard, so its disorder is too small because it is very strong. Then graphite also, calcium. But if you recognize very well, the entropy values of gases are actually very high because they can move very fast. And remember, we are talking about disorder. We are talking about what? Disorder. So we're going to say, when you're looking at these entropy values, it is very important to note about the following, that entropy values increase in the following order. So it may not be a constant, but to a large extent it is true. Normally solids have less disorder compared to liquids, compared to gases. We can compare this with our what we talked about, the different states of matter. You know, when solids are fixed positions, so their movement is very hard. Then liquids are somehow, they move. Their molecules are not very close to themselves. Then gases are far from themselves, so they can move at a faster rate. So this is why we can say that if you look at our table here, you observe that solids, if you look at the solids, they have lower entropy values compared to when we have gases. So if it is carbon dioxide in solid state, it will have a lower entropy values than when it is in gaseous what? State. So it's good to note that when you are dealing with entropy, then simple substances with fewer atoms have low entropy values because they can move faster. Yeah. So you observe that calcium carbonate has a higher entropy value than calcium. So here we say, yeah, you're saying that simpler substances with few atoms have low entropy values than complex what? Substances. So we observe that these ones which have more atoms, like for example, calcium carbonate has a higher entropy value than calcium what? Oxide, obviously because it has more atoms. And we imagine that the more the atoms, the faster they move. Then carbon dioxide, despite the fact it has more atoms, and then you will have a higher entropy value than carbon monoxide. We can go and look in our table here. If you look at calcium carbonate here, it's 92.9, and calcium oxide 39.7. So you see, then we can also go, the harder substances have lower entropy values than softer ones. We compare diamond and graphite. So if you look at diamond, it's called the hardest substance. So it has 2.4 and graphite 5.7. You see, somehow. So the harder it is, the more complicated for the molecules to move, and the lower the entropy values. So we have a simple exercise here. Explain the difference in the entropy values. You see bromine, naturally bromine is a liquid in its normal physical state, and iodine is a solid in its normal physical state. So you'll observe that bromine has a higher entropy value than iodine. That's the first observation. That is the first observation. Then one is liquid, another one is solid. So because bromine is a liquid, it will have a higher entropy value compared to the iodine, which is solid. Hence, you will have a lower entropy value. Then, for example, hydrogen. Hydrogen has 76, and this one has 186. So again, there is a statement we have made. We have said the simpler ones. This is simple compared to this one. So you see this one has more hydrogen molecules, so it will have a higher entropy value compared to this one, which has only hydrogen. Then for each of the following reactions, hope you are following, suggest and explain whether the entropy of reactants or products will be greater. Which one will be greater? So here we can compare ammonia gas, HCl gas, and this one solid. Obviously, here we are going to say that the entropy of reactants is higher than that one of products. Why? Because if you look at the left-hand side of our equation, we have more gases. We have what? More gases. Then let's look at also sulfur. This is sulfur liquid and the oxygen gas, then sulfur dioxide gas. So this is somehow complicated, but again we can say the one which has more gaseous molecules. The one which has more gaseous molecules. So probably here we can say that sulfur dioxide will have a higher entropy value, because it has sulfur and oxygen, more complicated than here when you have only oxygen. Probably here it will be more explanatory if sulfur was a solid, because it is naturally a solid. Then here we go to here, we have magnesium plus carbon dioxide giving us. So you observe here, again we are going to say reactants will have a higher entropy value. Why? Because we have here solid and gas. Here we have solid and solid. So we continue. So this summarizes our discussion here, and we are going to continue with our calculations involving total entropy change. Yeah. So we are going to say that if we want to find the entropy of a system, entropy of a we are going to do some simple discussion here. Entropy of a system will equal to the total entropy, will equal to the entropy is equal to, this we are talking about here, I'm going to say is equal to the entropy here of the system. Now we are used to using energy because of our previous topic, plus change in entropy of what? Of surrounding. So you excuse me because of the previous lesson, we are using to writing H. So we have here this, then plus entropy of what? Surrounding. So the total entropy will equal to this one. Let's write surrounding, but we can leave it like this, or we write it in full. Surrounding. So that's our entropy. So then we can be able to get the entropy of the system. System meaning what is taking place in the reaction. So I can say system, or I can write it in short form, will equal to the change in entropy for products minus change in entropy for reactants. So here we have change in entropy for what? Reactants. Yeah. Then if you want to get the change in entropy for the surrounding, which say here, I'm going to use surrounding like this, just to make it smaller, or we can write the whole of it. So we'll equal to, so we are going to say delta H, change in heat, negative over for the reaction temperature. So here we are going to say the standard enthalpy change, and then the temperature, which is standard temperature. We normally use this one as normally T is 298 Kelvin. So that will be. So if you want to get the total entropy, we can even write like this total. We may write in short form. Is equal to entropy of the system plus change in entropy of the surrounding. And this is how we get our entropy values. The one for system is products minus reactants. Then this one is negative change in the heat of reaction divided by what? The temperature. So because they are standard units, use temperature as 298 Kelvin. Yeah. 298 what? Kelvin. So from there, we can substitute in, and we have our, this one, change in entropy. I'm going to use this word to mean total, which will equal to change in entropy for system. I'm going to use like this, and do like this. Okay, let's write the whole of it. Minus, I'm going to substitute the other value, which is delta H over what? T, standard value for heat of what? Reaction. So we can do like this. When we normally do like this, it says students should note that. Then from there, we go and briefly talk about the Gibbs free energy. Gibbs free energy is the energy term used to determine the feasibility of a reaction. So someone may ask, what is feasibility of reaction? It's just to predict whether the reaction is possible or is not what? Possible. So, but Gibbs free energy is given by, we are going to say that Gibbs free energy, delta G, is given by negative change in entropy total times T, and say times what? T, or we can say is equal to negative T, change in entropy total, this Gibbs free energy. So using this equation, we can get another expression for Gibbs free what? Energy. By saying that I'm going to get this T and multiply it through here, so I'll have T total, which is equal, come and set T again. Yeah, thank you very much. This system minus this one. So hope you are enjoying our lesson, despite the fact that we have changed our disorder into equations. So then entropy, this entropy here is the relationship between this and this. The difference is the negative. So we can decide to multiply it through by what? A negative. So when we multiply it through by a negative, we shall have something like this. Total equals to negative system, and becomes positive. Change in what? To reaction. So we are going to say that this is actually the same as delta G. Gibbs free energy will equal to, I'm going to first write this one, then minus this one. So this is what? How you can get Gibbs free what? Energy. Another way to get Gibbs free what? Energy. But remember, we have some of these. So this heat of reaction, we can get it from the knowledge we talked about in thermochemistry, or when we talked about the different calculations of heats of reaction. Then this one of system also can be got from the data given, and temperature is 298 what? Kelvin. So from there, we can continue. You can look at your screen. We are going to say how to use Gibbs free energy to determine the feasibility of reaction. So we are going to say that when we have delta G, Gibbs free energy total, let's call it total or like this. If it is negative, so G, if it is negative, we say reaction is possible. The reaction is possible. It is what? Possible. It's possible. Or we say spontaneous. You can look at your, we say possible, feasible, or spontaneous. If it is negative. If delta G is positive, it means the reaction is not possible. The reason I'm writing it, I want you to get it. Is not what? Possible. So when you say not possible, again we can say not what? Feasible. Or there is that thing which sounds very nice. We normally call it non-spontaneous. Spontaneous. So meaning it cannot occur on its what? Own. Yeah. So we are saying here, if we say this is negative, means delta G is less than 0. If it is positive, it means delta G is greater than what? 0. So if it is less than 0, then this one will be negative. If it is, so it means here we shall have negative delta G. Here we shall have positive what? Delta what? G. So for standard values, we normally put this thing here for standard units. And sometimes to be specific, we can put total here. To be specific, because even this one can give free what? Energy. So then there is something we want to talk about, which we are going to be using in our calculations, saying that to determine if the temperature determine the temperature at which the reaction is feasible. Temperature at which the reaction is what? Feasible. We can calculate it from saying that at the point we have an expression here. We have delta G total. The temperature at which our reaction is what? Feasible. So we have here, we can use a duster here, our cheap duster. So we say delta H. I'm going to use this equation here. Delta H R minus T delta S like that system. So we can say if we want to determine the temperature at which our reaction is feasible, we can say delta G, that temperature will be 0. Will be what? This one will be 0. Will be what? 0. At which the reaction is feasible, or the temperature at which the reaction is possible. So we can say above the reaction is possible. So we can say delta T should be less than what? 0. At which the reaction is not possible. Delta T greater than what? 0. So temperature at which the reaction is possible is equal to 0. Times the temperature at which the reaction is possible, again we can say less than what? 0. Then at which the reaction is not possible, we say greater than 0. So where we have this one, you're going to put 0, then we shall have delta H R minus T, delta H system. System, I've remained writing this system. So we say T, I'm going to say our T will be equal to this one over this one. System. So we can use this expression when you are determining temperature at which the reaction is possible. The reaction is possible, or temperature at which the reaction is possible, or temperature at which the reaction, above which the reaction will not be possible. Temperature below which the reaction will be possible, temperature at which the reaction is possible. Reaction is what? Possible. So, as you said that if delta G is negative, the reaction is what? Possible. If it is positive, the reaction is impossible. Yeah. So we are going to look at our worked example. He's saying that using the data below, hope you are following, calculate the standard enthalpy. So if you look at our data, they have given us the standard enthalpy. You look at your screen, the standard enthalpies of formation. So if you want to get the standard enthalpy of reaction above, we normally say, if you remember very well what we discussed in the heats of reaction, we say A, that our enthalpy of reaction, delta E, will equal to change in enthalpies for products, because we have enthalpies of formation, minus change in enthalpy for reactants. So these are enthalpies of formation, if you remember. So we have oxygen, which is 0, and chlorine, which is what? 0. So we are going to use our product of water. We said 2 times negative 2, 4, 2, minus 4 times the 1 of HCl, which is negative what? 90 what? 2. So we can calculate very quickly. So 2 times negative 2, 4, 2, plus 4 times 92. So our answer will be negative 116 kilojoules per what? Per mole. So units are in kilowatt joules. Then we go to our entropy. The entropy change for reaction. So we are going to look at for the system. We are going to call it the entropy change for the system. Entropy change for the system. So entropy change for the system, we have this one will equal to change in entropy. Change in what? In entropy. Change in entropy here. Change in entropy for products. Minus change in entropy for reactants. Reactants, yeah. So we're going to substitute very quickly. So we say 2 times 2, 3, plus 2 times 189 minus 4 times 187 plus 205. Yeah. So we can say the randomness. It's good for us to put brackets here. Brackets. So 2 times 2. So the entropy, all of them have values. They are not like heats of reaction, where we say that the enthalpy of formation for elements is 0. So we have negative 1, 2, 9. Here we have joules per watt and more. So all of the values, all our values are actually negative. So then calculate the temperature at which the reaction is feasible. So we are going to use this one. We are going to see T. We are going to say that our T will be equal to change in reaction over change in what? This one. So we have negative 116. Yeah, because they are kilos, we're going to multiply times 1,000. And here, down here, we have only joules. Joules per mole. 120 what? 9. They are all negative values. All negative what? Values. All negative what? Values. So, we are going to say that 116 times 1,000 divided by 120 what? 9. 116 divided by 120 what? 9. So times 1,000. So our value will be, our temperature will be 9.2 Kelvin. That will be what? Kelvin. Yeah. Then finally, that's our temperature. So we are going to say that deduce the effect of increase in temperature to the position of what? Equilibrium. So when you are deducing the effect of temperature, we look at our value for heat of reaction, which is if it is positive, we say the equilibrium position. You look at our senior forward. If it is positive, we say that the reaction will shift to the forward direction. If it is negative, that is if the exothermic, we say the reaction will shift to the backward what? Reaction. So next time we shall look at more questions about this. Thank you for following me today. Hope you've got something on our entropy values, and we shall meet next time. God bless you very much.